Okay, Jai Hind dear students, myself Alok Kumar, and today we will discuss the stability factor and DC biasing of BJT. So before starting, first we will discuss what is stability factor, why we calculate stability factor, and what is the need of DC biasing of BJT, right? So as we know, we calculate the Q point, right? So Q point or quiescent point, which tells that in which region our BJT is operating. Okay, so by Q point we can tell in which region our BJT is operating, and that Q point should lie on the DC load line. So first of all we should draw the DC load line, then we locate the Q point. Then due to several reasons like thermal runaway and due to change in parameter beta, so this Q point may vary. It may go into saturation region or it may go into the cutoff region, right? So for example, if we have, if I draw the characteristics, so first of all, if I draw the characteristics, output characteristics of BJT, suppose here we have output current IC, and if we are drawing it for a common emitter transistor, common emitter configuration, then here this voltage should be VCE, right? And the output characteristics we will get like this. Right, so we know that this region is called saturation region, this region is called saturation region, and then this region is called cutoff region, again this region is called active region, this region is active region, right? So if we draw the DC load line, then it should be like this. Okay, so here we will have IC saturation, here we will have VCE saturation, right? And our Q point should be on this DC load line. So logically it should be in the middle of this DC load line. Here we should have our Q point. Q point is nothing but the value of IC and VCE. So we can say Q point is nothing but the value of IC and VCE, what the circuit is providing. Okay. So, but as we know, the output current equation of this common emitter configuration can be given as IC is equal to beta times IB plus ICO, right? So this is the output current equation for the common emitter configuration. IC is the output current, beta is the gain, and IB is the input current, and ICO we can say it is the saturation current. When input voltage we have open circuited, and then the current that is flowing through the transistor, it is called saturation current, ICO. Okay, in this equation we can see this IC is depending on this ICO and this factor IB, this factor beta, right? So this ICO is called saturation current. ICO is nothing but your saturation current. Okay, and we know in diode we have studied that the saturation current strongly depends on the temperature. It gets double at every 10 degrees C rise in temperature. So when the temperature will increase, this ICO current will increase, right? Because it is strongly depending on the temperature, gets double at every 10 degrees C rise in temperature. So when temperature will increase, this ICO will increase, and here we can see if this ICO is increasing, then IC will increase, right? So this is one factor, and if IC is increasing, it will further increase. If IC is increasing, it will further increase the temperature. It will further increase the temperature. So you can say here this is a cycle will start, and finally your transistor will burn out. This condition is called thermal runaway, right? So one factor is this, that IC is changing, IC is continuously changing, right, due to temperature. Second factor is due to this beta, because we cannot have identical transistors which have same beta. So due to this beta also IC will change. So here Q point if we talk about this Q point, it is depending on IC and VCE, and if IC is continuously changing, then this Q point cannot be stable. It will also change, right? So this Q point will vary. Either it will go to the saturation region, towards the saturation region, or either it will go towards the cutoff region. And in the saturation or cutoff region, or output signal will get distorted. So we are trying to stabilize this Q point, right? So that's why we are using DC biasing. That's why we perform DC biasing of the BJT, because this Q point is not stable, and to stabilize this Q point, we perform the DC biasing, or we use the DC biasing, right? But after using DC biasing, how we can calculate that our circuit is stable or not, right? So for that we use stability factor, right? So for that we use stability factor. So we denote it by S, and S can be given as S is equal to DIC over DICU. That is how much change we are getting in output current, collector current IC with respect to change in saturation current ICU. So if we calculate this, then we can calculate the stability factor, right? So we know, so to first of all we will try to find out the general expression of this stability factor that we can apply on any biasing method and calculate the stability. So to start with, we will start IC is equal to beta IB plus ICO, right? And one equation that we have studied, that ICEO is equal to beta plus 1 into ICBO, right? So here if I modify this equation for, this is for common emitter configuration, right? So I can write IC is equal to beta times IB plus ICEO, and this ICEO can be replaced with this equation. So IC will be is equal to beta times IB plus beta plus 1 into ICBO, and this ICBO I can write it as only ICO. So this IC will be is equal to beta IB plus beta plus 1 into ICO in general form. Now if I differentiate this equation, DIC over DICO, so what I will get? I will get beta times DIB. I should differentiate it with respect to IC, okay, with respect to IC. So if I differentiate this equation with respect to IC, so here I will get 1 is equal to beta times DIB over DIC plus beta plus 1 into DICO over DIC, right? Now I have to find this term, right? So I can write it as 1 minus beta times DIB over DIC is equal to beta plus 1 into DICO with respect to IC, change in IC, right? So calculate this term, DICO over DIC, it will be is equal to 1 minus beta times DIB over DIC divided by beta plus 1, and this is nothing but inverse of stability factor. So 1 upon S is equal to 1 minus beta times DIB over DIC divided by beta plus 1, and so stability factor will be S is equal to beta plus 1 divided by 1 minus beta times DIB over DIC. So this is the general form, or we can say general expression to calculate the stability factor, right? So in any biasing method, when we perform the analysis, so we will use this formula or the expression to calculate the stability factor of that circuit, right? Now we will move to the next topic, that is DC biasing of BJT. DC biasing of BJT, right? So in this topic, basically we have 4 different biasing methods. So we will discuss one by one. So we will start with fixed bias. So we have 4 biasing methods. First of all, we will list them out. First is fixed bias method. Second is emitter to base bias, Next is collector feedback or collector to base bias. Or simply we can say this one is emitter bias method. Okay, and last one is voltage divider, or we can say self bias method. Why we call it self bias, we will explain or we will discuss, right? So out of these 4 methods, voltage divider is, we can say, the highly stable, because lower the stability factor, higher will be the stability. So the stability factor we will get for this voltage divider is lower as compared to the above 3 methods, right? So we will calculate one by one. So first of all, we will start with fixed bias. Fixed bias method. So if we draw the circuit, so here we have our DC supply, that is plus VCC, this is resistance RB, this is resistance RC. Here we have our collector terminal, this one is your base terminal, and here you have your collector terminal, right? The current flowing through this will be IB, here the IE current is flowing, and from here the IC current is flowing, and here the voltage is VCE, right? So first of all, to perform the DC biasing, we will remove these capacitors, because we know for DC biasing or for DC voltage, XC XC can be given as 1 upon 2 pi FC, and for DC biasing this frequency will be 0, right? So XC will be infinite. So these capacitors will behave like an open circuit in case of DC biasing, right? So we will remove these capacitors. Okay, so if I remove these capacitors, then the circuit will be like this. These capacitors will be open circuited. So the circuit is, now the circuit is this one. Now what we have to do, we have to apply KVL at input side and we have to apply KVL at output side. This is our input side, this is nothing but input side, and this one is your output side. So if I apply KVL at input side, then what I will get, this total voltage is VCC, then it will be is equal to VCC is equal to the current flowing through this resistance is IB, right? So VCC will be is equal to IBRB plus the voltage drop between base and emitter, suppose it is VBE, right? So VCC will be is equal to IBRB plus VBE. So this will be the equation for the input side. So I can write that VCC will be is equal to IBRB plus VBE, right? This will be the equation. From here I can get IB. IB will be is equal to VCC minus VBE upon RB. This will be the base current equation, and with using this equation we can find the output current, that is collector current. Okay, so IC will be is equal to beta times IB, or we can say beta times VCC minus VBE upon RB, right? So this will be the collector current IC, right? Then we can apply the KVL at output side, and output side we can calculate, we can write the equation. VCC will be is equal to ICRC plus this voltage drop VCE. Okay. So if we apply KCL at output side, then we will have VCC is equal to ICRC plus VCE, and from here we can calculate this VCE. So VCE will be is equal to VCC minus ICRC. So this will be the, we can say, output voltage, this is the output current. So finally what we have calculated, we have calculated the Q point, IC and VCE, value of IC and VCE, or we can say, here we can say this is ICQ and this is VCQ. It will represent the, that we are calculating the Q point, IC and VCE value, right. Now if we want to find out the stability of this circuit, so we have to use the stability factor. Then formula of stability factor is S is equal to beta plus 1 divided by 1 minus beta times DIB over DIC. This is the formula that we have proved. So here we have to calculate the value of this DIB over DIC. So IB, in this fixed bias we have calculated IB is equal to VCC minus VB upon RB, or it can be written as VCC upon RB minus VBE upon RB. So using this equation, if I calculate, if I differentiate this equation with respect to IC, then what I will get? So if I calculate DIB over DIC, that is if we differentiate this equation with respect to IC, so it will be 0. So the stability factor in this case will be S is equal to beta plus 1 divided by 1 minus beta into 0, or it will be is equal to, simply we can say beta plus 1. So S is equal to beta plus 1, right. So this is the stability factor of fixed bias circuit. What is beta? Beta is the current again, and we know the value of beta is very high. It may be 100, it may be 150, it may be 200. So the stability factor is also very high, right. The ideal value for this stability factor is 1, and what we are getting? We are getting larger than 1 value. So the stability factor is very high for fixed bias circuit. So that means we can say the fixed bias circuit is not a good circuit. Okay, it is not a stable circuit. Then we will move to the next biasing method, that is ammeter to base bias. Or ammeter bias simply. So in this, if we draw the circuit, then there will be only one change, that we will apply a resistance at the ammeter. Okay, so here also we will apply a resistance, right. So this is your plus VCC, this is your RC, this is your RB, and here you have your base terminal, here collector terminal, here ammeter terminal. Here obviously IB current is flowing, here again IC current is flowing, and here we know this IE current is flowing, and this resistance is called RE. The voltage drop between base and ammeter is VBE, right, and the voltage drop between collector and ammeter is VCE, right. So same methodology we will follow. First of all, we will apply KVL at output side. This is your output side. Then we will apply on input side. Then we will apply on output side, right. So this one is your input side, and here this is your output side, right. So first of all, we will apply KVL this side and then that side. So if I write the equation, so VCC will be is equal to IB RB plus VBE plus IE RE at input side. Okay. Now first of all, our aim is to find the Q point, that is we are interested in to find out the value of IC and VCE, right. So for that I want to calculate this IB value, but here we have IE also, so we will change this IE in terms of IB. Okay, so we can write VCC is equal to IB RB plus VBE plus beta plus 1 times IB into RE. Okay. Now IB we can take common and we can find the value of IB. IB will be is equal to VCC minus VBE divided by RB plus beta plus 1 into RE. And as we know beta is very greater than 1, so we can neglect this one also. So IB will be is equal to VCC minus VBE divided by RB plus beta times RE, right. So this will be the value of IB. Once we have the value of IB, we can calculate IC. IC is equal to beta times IB. With this relation we can find the value of IC. Once we have calculated IC, then we can apply KVL at output side and we can find the value of VCE. So at output side the equation will be VCC is equal to ICRC plus VCE plus IE RE, right. And as we know IE is approximately is equal to IC. As we know that IE is nothing but approximately equal to IC. Okay. So here I can replace this IE by IC and then we can find the VCE. So VCE will be is equal to VCC minus IC, we can take common and it will be RC plus RE. So this will be the value of VCE. So we have calculated the Q point. We can say this is nothing but ICQ and this is nothing but VCEQ, right. Now next target is to calculate the stability factor of this circuit. So for that again we will use that formula. S is equal to beta plus 1 divided by 1 minus beta times DIB over DIC. So we need to calculate this value DIB over DIC. For this what we need to do, we want input side equation, right, and input side equation was VCC is equal to IBRB plus VBE plus IE RE. And in previous slide what we have done, we have changed this IE into beta plus 1 IB, but now here I will change this IE, I will break this IE into IC plus IB, right. So we will write VCC is equal to IBRB plus VBE plus this IE can be written as IC plus IB into RE, right. Now this VCC is equal to IBRB plus VBE plus this equation, this term can be written as IC into RE plus IB into RE, right. Now we can take IB common and further we can write it as VCC is equal to IB into RB plus RE plus VBE plus IC into RE. Now if I differentiate this equation with respect to IC, because what we need to calculate IB DIB over DIC, right. So if I differentiate this equation with respect to IC, so what I will get, 0 is equal to DIB over DIC into RB plus RE, right, plus 0 plus RE. So the value of this DIB over DIC will be DIB over DIC will be is equal to minus RE upon RB plus RE, right, or it can also be written as DIB over DIC is equal to minus 1 upon 1 plus RB upon RE. So this will be the value. Now if you put this value into the stability factor, so S will be is equal to beta plus 1 divided by 1 minus will be plus 1 plus beta into 1 upon 1 plus RB upon RE. right? Or we can say S will be is equal to 1 plus RB upon RE into beta plus 1 divided by 1 plus beta plus RB upon RE, right? So this will be the final value of stability factor. And you can analyze, or you can see that this in this circuit obviously the stability factor will be less than the beta plus 1. Here from this equation you can see the beta plus 1, the factor beta plus 1 is divided by some factor, okay. So obviously this stability factor will be lower than the previous one, right? In previous case in fixed bias what we are getting, S is equal to beta plus 1, and now this beta plus 1 is divided by some by a term, right? So obviously the stability factor will be lower in this case, right? Now next case is, third case is collector feedback. Collector feedback configuration, okay. Collector feedback configuration. And if I draw the circuit, then it will be so this is resistance RB, this is RC, here we have plus VCC, this is nothing but base terminal, collector terminal, emitter terminal, this resistance is RE, again here IB current is flowing, here IC current is flowing, and from here IB plus IC current is flowing, okay. And here the voltage drop will be VBE, and here the voltage drop will be VCE, right? So again we will apply KVL at input side and KVL at output side. So if you apply KVL at input side, what we will get? We will get VCC is equal to IB plus IC into RC plus IBRB plus VBE plus IERE, right? So in this equation we can see we have term of IC also, we have term of IE also, all these terms we will convert into IB, okay. So we will write VCC is equal to IB plus beta times IB, because ICE will be is equal to beta times IB, and here into RC plus IBRB plus VBE plus this IE can be written as beta plus 1 into IB into RE, okay. Now if I take IB common, so VCC minus VBE, it will be is equal to IB we can take common, so one by one we will take. So IB here if I take common, then here I will get beta plus 1 into RC plus IBRB plus, and here it is beta plus 1 into IB into RE, okay. Now after simplifying this we can write IB we can take common, then it will be beta plus 1 into RC plus RB plus beta plus 1 into RE, okay. Or IB will be is equal to finally we can say VCC minus VBE divided by RB plus beta plus 1 into RC plus RE. Okay. So we can neglect this one, as we know beta is very, very large. So finally IB will be, we can say IB will be VCC minus VBE divided by RB plus beta times RC plus RE. Okay, so this will be IB. Now we can calculate IC. After this we can calculate IC. IC will be is equal to beta times IB, we know, and then we can apply KVL at output side. From output side we will get VCC is equal to IB plus IC into RC plus VCE plus IERE. Okay. In this equation we can neglect this IB. First of all, we can neglect this IB, and this IE can be written as in terms of IC. IE will be approximately is equal to IC. Okay. So after this, after applying these assumptions, so we can write IC into RC plus VCE plus ICRE. Okay, and then we can find the VCE. So VCE will be is equal to VCC minus IC, we can take common, and it will be RC plus RE. Okay, so this will be the final value of VCE. And to find the stability factor, again we can use the formula S is equal to beta plus 1 divided by 1 minus beta times DIB over DIC. To calculate this value DIB over DIC, we want our input side equation, and input side equation was VCC minus VBE is equal to IB plus IC into RC plus IBRB plus IERE. Okay, this was the original equation. Now here in this term IE can be replaced by IC plus IB. So we can write VCC minus VBE is equal to IB plus IC into RC plus IB into RB plus IB plus IC into RE. Now if we separate out this IB and IC terms, so this equation can be written as VCC minus VBE, it will be is equal to IB, if I take common, then it will be RC plus RB plus RE. Okay, and if I take IC common, then it will be RC plus RE. Right. Now if I differentiate this equation with respect to IC, what I will get? 0 is equal to DIB over DIC into RB plus RC plus RE, okay, plus RC plus RE, right. And from here this DIB over DIC will be is equal to minus RC plus RE divided by RB plus RC plus RE. So if I put this value into this formula, I can get the stability factor. So this is the way how we can find the stability factor, and before implementing we can tell about the circuit, that this circuit will be stable or not, or how much stable it will be. Ideal value of the stability factor is 1, and if it is near about to 1, then we can say the circuit will be stable, and otherwise we will do the more changes. So the next configuration will be the voltage divider configuration, that we will discuss in the next lecture. Okay, thank you.